Uh, we would like to invite the next speaker is Marc Gasbarro from NOAA, and it's also invited talk.
Thank you, and excellent talk, Erin. Very good conversations and good segue into what we did here at NOAA NESDIS Commercial Data Program. I work with Natalie Laudier and Jerry Peltzer. You've heard from them earlier in the week. And I worked on the Space Weather Data Pilot Project, now concluded, and we're going to talk about that here today. Ooh, this thing went all the way forward. I don't know what happened here. Okay, great. So, hold on here. I apologize. Great, here we go. So here's the agenda we're going to talk about today. Okay, we're going to talk about the pilot data overview and review, some findings and results, talk about products and use cases, and wrap up with summary and recommendations. There we go. Now I got it. Okay, so why is commercial space weather data necessary? The bottom line, folks, is that Cosmic 2 is not enough. Cosmic 2 can see up to approximately 40 degrees north-south latitude. So above that, you need something else to fill those gaps in. Commercial satellites provide high-rate GNSS-derived data when a sudden scintillation event is detected, and they can also measure TEC. And we're going to talk about that here today. This is necessary because it's critical for GNSS applications when a storm, such as what we saw back in August or May, can induce errors of tens of meters in cases when precision is needed down to the millimeter level. So this is very important stuff. Okay, so we had the award, started in 2022, and it was for a 12-month pilot. We had 3 vendors on there, but we're not going to get into geo-optics here, but 2 vendors, Planet IQ and Spire Global, were the 2 ones that participated in the pilot and remained with us throughout the duration. So pilot measurements. Okay, so what did we measure? TEC, total electron content and scintillation. TEC is approximately the number of electrons encountered by a GNSS signal along the path. Those observations help specify the electron density structure in the ionosphere. From there, you can get profiles, and these tracks are 8 minutes or longer. That was the specification in the statement of work. They're typically low rate, 1 hertz, and we do have some accuracy specification to that as well. Scintillation refers to the rapid localized fluctuations in the ionospheric state, okay, and affects both the power and the phase of the signal, the radio signals propagating through the ionosphere. And this is even more severe than TEC, where with TEC, you can have a dual frequency GNSS user that can kind of engineer their way around TEC problems, sort of. You can't do that with scintillation. Loss of lock is a problem. Okay, we measure this by 2 indices, scintillation phase and amplitude. Measurements must be high rate, greater than 50 hertz, in order to capture the rapid changes. And we're going to talk about this S4 scintillation phase, scintillation amplitude threshold of 0.2, because that was a problem during the pilot. Okay, and latency 30 minutes. We did require that. I want to thank everybody right now who participated in the Space Weather Pilot team. Many of these agencies are in the audience today. I especially want to thank the Space Weather Prediction Center, who were the ones that actually led the technical team for this entire pilot, UCAR for processing the data, and everybody else for doing all the other work, including our vendors. So thank you very much. Okay, so let's get into the findings. Okay, TEC and electron density profile data validation. We see very good valid data validation when we compare against Cosmic 2. Okay, and we do that by looking at the F2 layer. And in your upper left-hand corner of the screen is Planet IQ's data co-located with Cosmic 2. On the right, Spire. And we're looking at the electron density peak density, and peak height within the F2 layer. And you can see an excellent correlation between the two. Down in the bottom left is the data validation with the Cosmic 2 TEC product. Again, both vendors, Planet IQ on the left, Spire on the right, did a very good job with that. Accuracy, we're looking for 4 TEC unit root mean squared. We didn't quite get there, but we're close. So, spatial temporal distribution of data. Now, I will say, caveat, this was back in early 23. Data delivery ended in April, May 2023, May. Okay, during the data delivery, Spire had 25 to 27 satellites on orbit. They don't have that many today, but that's what they had then. So you have to take this with a grain of salt. Planet IQ had one satellite that was pretty much only one during most of the pilot, although for a period of time we used NOMS 2 and NOMS 3. On this slide here, you can see pretty good spatial correlation or distribution, excuse me. Temporally, again, it really depends upon your diversity of orbits and the amount of satellites you have up on there. So, okay, so both vendors did an excellent job. Where the two vendors kind of separated themselves was latency. Now, I want to talk about latency just a little bit here. So, for the statement of work, we put in there 30 minutes from satellite down to NCCF. That's the NESDIS Common Cloud Framework, which is where we ingest the data, secure ingest. Okay, so that requirement from satellite to ingest is 30 minutes. Spire met that. Don't forget, though, they had about 25 to 27 satellites during that time frame. Okay, Planet IQ probably had 1 to 2, depending upon when we're looking at throughout the pilot. Okay, take that into account. Now, we got about 3 minutes data flow from the NCCF to UCAR. We're assuming that it's probably not quite 3 minutes, but that's an assumption. And then we have the data processing that UCAR does. Now, you see that it took more than 3 times the amount of effort to process Spire data than in Planet IQ. Why is that? Both vendors package the data differently. Planet IQ sent data in continuous streams, which is what we want to see. At the time, Spire sent data in discrete 1-minute segments with varying latency, and then added time to process the data. That's what the UCAR team had to do. Now, I will say, in conversations with Spire post-pilot, they are willing to switch to a continuous data stream. So if we were to do another pilot, I don't think this would be an issue on their end. So what this means is continued collaboration between CDP, our program office, UCAR, and the vendors. And even though you see 9 minutes for Planet IQ, we still think that we can improve upon that. And that's not just in the vendor side, it's also on UCAR side when they process data. The vendors and UCAR process data just a little bit differently. So I think everybody's on board with trying to come together to find a common solution going forward. This is definitely workable, and if we were to do another pilot, I think a lot of this will be solved, at least on the processing side. Okay, so TEC impact assessment and coverage. TEC, as we see from our RO, improves global coverage. So on the upper left-hand corner slide, that's the Aglotech model observation density with just the ground data. The bottom left is when you ingest all RO data to include Cosmic 2. So there's a pretty big disparity on there. On the right, impact analysis with RO data. So what we want to see here is that away from ground stations, that there's a greater impact, a greater sensitivity into the Aglotech model. So when we ingest RO into here, and this was for this particular time frame on this graph, we just ingested the Spire data, but it would be the same with any commercial provider. Did it provide benefit? And the answer is yes. We saw greater sensitivity, greater impact away from the ground stations. That is what we want to see. So the bottom line is it improves model performance and is very useful to TEC products. Let's switch to scintillation. Okay, so scintillation is not the same globally. Equatorial scintillation behaves different than high latitude scintillation. Both regions differ in magnitude field geometry. Okay, so I'm not going to get into all the physics of the ionosphere because I don't know all the details. I'm not a space physics scientist, though I've learned a lot. But the plasma bubbles are oriented and behave very differently in the equatorial regions with a more vertical structure, more typical post-sunset peak. With the high latitudes, it's oriented more horizontally. Gradients are stronger, and it's also experiences a more rapid drift. The density altitudes are also different. It's important to note that during this pilot, the Cosmic 2 CalVal only addressed the low latitude scintillation data. Why? Because there's no other government provided platform in which to measure against in the polar regions, at least not yet. So this was the first comprehensive analysis and research on measuring high latitude scintillation with GNSS RO data. So this truly was truly was groundbreaking. Incidentally, when MEDUP launches in a couple of years, they will be able to see, close to 600 kilometers, 500 to 600 kilometers. So that would be an interesting data point to validate against at some point in the future. All right, so going on to the findings with scintillation, geolocation. I don't need to explain how geolocation works for an RO path here. To this audience, we use tangent points. Scintillation, it works a little differently. Scintillation can occur anywhere along our RO gray path. Also, the two regions, equatorial and polar, behave differently, which also affects how you measure geolocation. So a geolocation scheme needs validation in order to properly determine where it is. So Boston College and UCAR developed some algorithms for low latitude region, and the Cosmic 2 validated the algorithm's performance. Both BC and UCAR performed assessment with the commercial RO data, but they could only do it for within the Cosmic 2 region. The data verified well, but the data set was limited. Bottom line, more work is needed. Okay, scintillation trigger algorithm. This was a big finding. Okay, the trigger algorithm of S4 greater than 0.2 was designed based off of the TGRS requirements for Cosmic 2. Cosmic 2 is in the equatorial regions. Okay, but that was too restrictive to get high rate scintillation data coming down from the polar regions. So to obtain scintillation from the polar regions, we asked the vendors to provide all data, not just data when an S2 S4 is triggered with 0.2, but to provide all data within a 72-hour window in May. And we did that because we just knew we're not seeing enough data from the polar regions. So when we did that limited data campaign, we found that the vendor data performed well in the low latitudes, and it confirmed that threshold with Cosmic 2 is adequate. In the high latitudes, the data show that scintillation events vary quite a bit, and that a lot of scintillation events occurred with much lower S4 values and even occurred with phase dominant signatures. Bottom line is that future triggering algorithms must take into account a potential lower scintillation and also phase dominant signatures. Detection of anomalous data is another thing. Okay, anomalous vendor data in RFI must be distinguished from scintillation because sometimes this anomalous data in RFI can manifest themselves to look like ionospheric scintillation. So methods need to be developed in a rather rapid manner to detect from real scintillation. So the University of Colorado and their team developed machine learning algorithms to identify spurious features and separate them from real scintillation. So a lot of work was performed with this machine learning technique, performed well, and also confirmed that vendors can indeed detect scintillation. Okay, we did a lot of work confirming with the vendors, ground communication times, antenna structure, you name it. So both vendors are very cooperative in providing us their technical information. Future work is needed to expand this, however, and also to investigate scintillation and geolocation algorithms to demonstrate sensitivity in relation to spurious features. Okay, so some use cases here. Now I want to caution here that the use cases, the user is SWPC, the Space Weather Prediction Center at NCEP. So we've worked very closely with them during this time frame. So right now on the left, one of the current use cases that they use is the ICAO mandated advisories. And you can see there in the left a kind of a screen capture of what that advisory map looks like from the geomagnetic storm. They also incorporate GLOTEC model data from ground and Cosmic 2. The future, though, is to also incorporate COM-RO. But again, latency really needs to be less than 30 minutes. For scintillation, similar thing. There's ICAO mandated advisory similar to TEC. The products, though, right now are built from ground receivers only. Future uses. Now, I will say that the products on here are now starting to get implemented, but not at SWPC at the moment. I think the plan is for them to use some of these products. So we have the bubble map and the all clear map, which were developed mostly with US Space Force funding through a program called Solar Max Sustainment that Aerospace Corporation is also on. And I believe Dr. Paul Strauss will talk a little bit more later on about some of the work that he's done. So NESDIS also provided some funding towards this as well. So this is a product that is being used at least for the DoD, and this hope is that SWPC would incorporate some variation of this at some point, and the indication is that they will. So what we're seeing in the upper right-hand corner is a bubble map, which indicates regions where scintillation causing plasma bubbles are occurring, and they tend to map longitudinally along the magnetic field lines. It's a one-dimensional map, though. The bottom right is all clear, and just as the name suggests, all clear. It's used for RFI attribution. Future work, though, is to expand this to L-band frequencies, and hopefully at some point in the future, I don't know when that will be, to incorporate commercial RO. All right, summary recommendations to wrap up. Both vendors were compliant and cooperative. We thank them, Planet IQ and Spire. The pilot team made substantial advancements and groundbreaking work with high latitude scintillation. TEC and high and low lat scintillation, not far from operational readiness. High lat scintillation needs a lot more extensive analysis, assessment, and evaluation. Our report is available, publicly available. When the slides get shared out publicly after this conference or workshop, you can click on that link and get a report. The NESDIS decision, unfortunately, was not to proceed to another pilot at this time. Its priorities, we only have so much money in a given year, and so that's just the unfortunate realities with certain budgets and resources. But that doesn't mean that our work is all for naught. A lot of great work went into this project, and we will continue to explore avenues to further ionospheric measurement readiness and incorporate this into future planning purposes in the future. So that is all I have for today, and I thank you very much for your time.
Thank you very much, Mark, for excellent overview of pilot project. We have time for a couple of questions.
Very nice talk. Thank you.
Yeah,
Thank you. Of your driving requirements that you showed early on was 1 millimeter of precision. I'm assuming for a single frequency GPS user. Can you confirm that was a driving metric for you?
I would not say that was a driving metric. We've just found that is what the users require. That's the millimeter.
Yeah. So
yes.
A use case that you were seriously considering is 1 millimeter single frequency precision.
So one example would be where measurements down to the millimeter level are needed is precision agriculture.
Absolutely.
So might have heard some of the reports back in May during the geomagnetic storm, but that storm was causing a lot of havoc to planters in the Midwest and the upper Great Plains. A lot of these machineries now run on precise GPS or GNSS signals, and they were not planting exactly where the seeds needed to get planted. So when farmers return back to that later on, they're not returning to the exact same location, even if it's centimeters off. That's a problem. So, yeah.
Thank you.
No problem. How did I know Jonathan was going to come up here? I could feel it.
You mind flipping back to the total electron content accuracy validation?
The latency?
Prior to that, the accuracy.
This one?
Earlier. That one. Is this based on the total electron content which was delivered, or was it based on total electron content which was separately derived? Okay.
Right by you, Carl.
Thank you, Jan.
It was separately derived. Now the next slide, please. With included the latency. Was this based on the total electron content which was delivered or separately derived?
Well, the latency right there on the far left was delivered to the NCCF.
That is incorrect. Planet IQ bid to deliver a completely calibrated total electron content product. We dropped latent data on the floor, which did not meet the latency specification. And this study is evaluating something which was completely separately derived, separate from the contract. We do not concur with your findings. The UCARTA SWPC latency spec should have been 0. The satellite to NCCF spec should have been 30 minutes because that's what we provided. Please.
Go ahead, John.
Could have given us that feedback. We didn't receive any feedback whatsoever.
We can talk offline later, Jonathan. We can talk with you, Carl, later on. I know we've had some conversations in the past about this, but
Maybe if I
Yeah.
may,
go ahead.
Very, very short.
very rich. A comment from the experience with neutral atmosphere commercial data. One of the problems is every data provider has to learn again how to process their data, and sometimes that takes time. Every data provider invents new algorithms to improve it. Every data provider is not open of what they are doing. That is, in the neutral atmosphere, we have learned that it's beneficial to process the data in a central way, just to ensure the consistency between missions and between data sets to make them comparable. And I think that was a very good decision. And I guess it is a very good thing to do in space weather as well. Thank you.
Thank you.
Thanks again, the speaker.
Okay, thank you.
And we are going to proceed to the next speaker is Qian Yao from UCAR. He will present our recent progress on sensing thermospheric density using Cosmic 2 satellites.